Free fall of a body can be defined as a body which is just released. What happens to the acceleration? We had told you that the acceleration remains constant at 9.8, is in the ratio of 1:3:5:7. Hello students, welcome to this third session on motion in a straight line. Chapter 2 from first PUC Physics. I am Madhu R from the Department of Physics at Vidhyaashram PU College, Mysuru, your temple of excellence. Let us try to recall what we did in the previous session. We studied about the position versus time graph, where we understood that the slope of position versus time will give me velocity. We studied the velocity time graph, where we understood that the slope of a VT graph will give me acceleration. We also understood that the area under the VT graph will give me displacement. We also understood the other significances of these graphs, and we derived the kinematic equations of motions. V is equal to V naught plus AT, X is equal to V naught T plus half AT square, and V square equals V naught square plus 2AX. Yes, we derived these equations with the help of the VT graph. Let us move on and try to understand the significance of motion under gravity, or what is generally called as free fall. Free fall of a body can be defined as a body which is just released near the surface of the earth. It is not somewhere in the orbit. A body which is released just near the surface of the earth. It moves towards the earth with nearly constant acceleration. The acceleration in this case shall be constant. If you neglect the resistance offered by air, then the motion of this body which is falling down is called as free fall. Any body which is coming downwards, okay, when you neglect the resistance offered by air, it can be called as a freely falling body. The acceleration of a freely falling body is called acceleration due to gravity. It is represented by G, and the value of G is considered generally to be 9.8 meter per second square. Okay, let us check when this acceleration due to gravity is considered to be positive and when it is negative. If you choose the downward direction, okay, if you choose the downward direction to be positive, why should you choose the downward direction to be positive? Because the gravitational force is acting towards the center of the earth. Okay, the gravitational force is generally acting towards the center of the earth. So if you consider the downward direction to be positive and the upward direction, anything beyond the surface of the earth, to be negative, the gravitational force will be positive if the object is stationary or it is moving downwards. So any freely falling body, G can be considered to be positive. It will be negative if the object is moving upwards. It is against the gravitational force. Let us try to understand how the equations will change. The kinematic equations will change under the effect of gravity. Okay, the motion of a freely falling body is in y direction, right? It is either vertically upwards or it is vertically downwards. What is the general convention? Any body moving upwards is generally considered positive. Any body moving upwards or rightwards is positive. Any body moving downwards or leftwards is considered negative. So whenever a body is freely falling, I will take A to be minus G. So under the acceleration due to gravity, your equations will be V is equal to V naught minus GT. Instead of the X direction in the previous class, here we are taking Y, because either the object is moving upwards or it is coming downwards, free fall. So this is V naught T minus half GT square. V square is equal to V naught square minus 2GY. Okay, wherever you had an A, we have replaced that with minus G. Please understand, whenever you are dropping a body downwards from this space, the initial velocity of that body will be 0. There is no velocity. I am just dropping some body from top to bottom. So what will be the equations now? V naught is 0, so V becomes minus GT. Once again, V naught is 0. It becomes minus half GT square. No initial velocity. V naught square becomes 0. V square equals minus 2GY. Okay? Is that understandable? How the kinematic equations behave when acceleration is replaced by gravity and when there is no initial velocity. These are the equations. Now let us try to understand the PT, VT and AT graph. What is this AT graph? This is acceleration versus time. Position versus time, velocity versus time and acceleration versus time for a freely falling body. When a body is falling freely, it generally follows the path of a parabola. So it will be a simple curve. The position versus time graph. What happens to the velocity? The velocity constantly increases. So it is pointed downwards because the body is coming downwards. It is taken in the negative axis. What happens to the acceleration? We had told you that the acceleration remains constant at 9.8. The acceleration of the freely falling body remains constant at 9.8. So you can observe a straight line in case of a versus T graph, AT graph for a freely falling body. Please remember, for a freely falling body, the PT graph is a smooth curve pointing downwards. The velocity versus time graph is a straight inclined line pointing downwards. The AT graph is a horizontal line at 9.8, at minus 9.8. Okay, so this could be a generally asked question in your examination papers regarding how the curve behaves for a freely falling body. Moving on, there is one more very important concept called as the stopping distance. How to understand this stopping distance? Imagine you are traveling by your vehicle on a highway. You observe some obstacle or hazard on the road at a distance. What do? You apply the brake. What does the vehicle do? It moves to a certain distance and then stop. Let us try and understand this once again. You observe an obstacle at some distance. Your eyes will observe. It sends a signal to the brain. The brain sends a signal either to your hand or to your vehicle or to your leg based on the vehicle. If it is a two-wheeler or a four-wheeler, you apply the brake. There is some time and distance involved before you react and apply the brake. This is called as reaction distance, or it can be called as reaction time. For the person who is applying the brake, it is the reaction time. For the moving vehicle, it becomes the reaction distance. You detect the hazard or the obstacle here. You apply the brake. After some time, the braking begins. The vehicle will move a certain distance and then ultimately stop. The car stops at this point. So this is called as the braking distance and the reaction time. Okay, let us check. When brakes are applied to a moving vehicle, the distance traveled before it stops is called as the stopping distance. Whatever is the distance it travels before it actually stops is the stopping distance. It is given by minus V naught square by 2a. Initial velocity, square of initial velocity by twice the acceleration in the negative form. That is the distance. Now what is this reaction time? When a situation demands our immediate action, you need to act immediately. It takes some time, a split of a second before you actually do that or you actually respond. That split second of a time can be called as reaction time. Depending on how quickly you respond, your reaction time can be smaller or larger. So that is regarding stopping distance and reaction time. Let us understand one very fascinating concept regarding how much distance is covered with every second of fall. You drop an object from the top of a building, it takes say 10 seconds to reach the ground. Okay, what is the distance traveled in each of those seconds? That is given by the equation Sn is equal to V naught plus half g into 2n minus 1, where n is time in seconds, where n is time in second. Okay, how do I understand this? We know the equations, right? Acceleration is generally at 9.8 meter per second, and it is meter per second square, and it is constant throughout the fall. What happens to the velocity? See, initially when you drop an object, the initial velocity will be 0. So for the 0th second, the velocity is 0. What happens to the distance traveled by the object? That also remains 0. Okay, here v is equal to v naught plus at, but v naught shall be 0. Initial velocity is 0. So v shall be equal to at. Sn will be equal to, once again, v naught is 0 in case of a freely falling body, half g into 2n minus 1. So what will happen in the first second? In the first second, it is acceleration into time. Acceleration is 9.8. Okay. What happens to the distance traveled? N is 1, so this is 2 minus 1. So this becomes g by 2. Or this becomes 4.9. What happens in the second second? Okay. From 9.8, I have a into t. 9.8 into 2 seconds. This becomes 19.6. What happens to the distance traveled? This becomes 2. So this becomes 3 by 2g. 3 into g by 2. Okay. Similarly, if I go to the next part, this will be 5 into g by 2, the distance traveled. Next second, it will be 7 into g by 2. So on and so forth. Galileo was the first one to observe this relation. Can you see this? Here it is g by 2, 1. Here it is 3 into g by 2, 3 times. Here it is 5 into g by 2, 5 times. Here it is 7 into g by 2, 7 times. So the distance covered by the object during the free fall is in the ratio of 1:3:5:7. This is called as Galileo's law of odd numbers. This could be a question in your competitive examination. The velocity keeps increasing during free fall because gravity exerts a constant downward pull, causing a steady, continuous acceleration. What does that mean? Near the Earth's surface, gravity is 9.8, which means that for every second the object falls, its velocity increases by 9.8 meter per second. You can observe here, at the 0th second it was 0, first second it becomes 9.8, during the second it becomes 19.6, so on and so forth. Okay, so this is regarding the distance covered in the nth second of fall. Using this equation, I can find out what was the distance covered by the body in 11th second or 13th second or 15th second, so on and so forth. Okay, now let us move on to the next interesting concept, which is regarding relative velocity. Until now, whatever we studied, it was regarding a stationary observer and a moving body. Okay, the observer was stationary, the body was moving with some velocity. Now we are taking into consideration two bodies. Okay, two bodies are in motion. What is the velocity of one body with respect to the other? What is the velocity of this blue car relative to this red car? So this is called as a relative velocity. Velocity of one body with respect to another moving body is called as relative velocity. Please observe, both the bodies are now in motion. If two bodies A and B are in motion and they are moving with velocities VA and VB in the same direction, they are moving in the same direction, relative velocity of A with respect to B is given by VAB is equal to VA minus VB. If you want the opposite, what is the relative velocity of B with respect to A? It is written as VBA, where it is VB minus VA. Okay. So whatever is the velocity of one moving body with respect to another moving body is considered as relative velocity. Suppose two persons are walking together with the same velocity. See, this VA will be equal to VB, which means that their relative velocity will become 0. That is why when two friends are walking together, they can easily speak with each other. They can easily converse with each other. That is what we try to tell you. If two bodies A and B are moving with velocities VA and VB in the opposite direction, you can check here. One is moving towards the south, other one is moving towards the north. Okay? So both are moving in opposite directions. Relative velocity of A with respect to B is VA minus VB. VB is already moving downwards, so it comes with a negative sign. It becomes VA plus VB. Suppose I want to check what is the relative velocity of B with respect to A. B is already with a negative sign, minus VA, minus of VB plus VA, which means that the relative velocities of both of them, the magnitude of relative velocities is the same, whereas the direction changes of the relative velocity. The relative velocity of A with respect to B will be in one direction, B with respect to A will be in the opposite direction, but their magnitude will be VB plus VA. Okay? Now let us check the simple concept of two friends walking with each other. Two bodies with equal velocities in same direction, which means that VA and VB are the same. They are both walking with the same velocity. They are moving in the same direction. What is the formula of relative velocity? VAB equals VA minus VB. But VA is equal to VB. So what will happen to the relative velocities? It becomes 0. So when two bodies are walking next to each other, it means that their relative velocity is 0. If they are walking at the same velocity in the same direction. Next, two bodies with unequal velocities, but they are walking in the same direction. Two unknown persons are walking past one another. They are overtaking one another. See here, one has started with some initial velocity and going slowly. One has started with a lower initial velocity but is moving at a faster pace. What will happen to the relative velocity? It remains the difference between the two velocities. If it is from A with respect to B, it is VA minus VB. If the relative velocity is B with respect to A, then it becomes VB minus VA. So this is an interesting topic which is called as relative velocity. Now we have come to the end of this module with terms to all the concepts. Have a wonderful learning experience. Thank you.